next, let's talk about kinetic molecular theory a little bit. Kinetic molecular theory, what does that mean? Well, it's a theory that's applied to molecular gases about why they move and how they move. And so the idea before was, oh, we can just relate pressures, volumes, temperatures, and moles and think about how they're related to each other. This one's more about the movement, the kinetic energy that something has. And so this theory really tries to figure out why your gases move, not the parameters that define their existence. So here are the postulates that our textbook has of the kinetic molecular theory. Particles are so small, they're in constant motion, no forces on each other, and then this average kinetic energy is assumed to be proportional to the temperature of the gas in Kelvin. What does these mean? Let's talk about each one specifically. Kinetic molecular theory number 1 states that the particles of gases are tiny compared to the spaces between them, which means if I'm asked for the whole volume of the container, do I need to subtract out the volume of an individual molecule of each gas molecule? No, because it's assumed that this huge space here is so big that the tiny little amount that my bromine takes up is not important as far as the whole volume is concerned. Whereas if you have a liquid, everything's a whole lot closer together, and so now we're thinking more about the volumes that the liquid themselves take up. It's sort of how, if you were to think about atomic theory, is the volume of an electron really that important compared to the volume of the entire atom? No, electrons are teeny tiny. Okay, and so the size of these individual atoms is not important to the total volume of the container. Kinetic molecular theory number 2. This one do kind of two things here. So first off, particles of gas are in constant rapid motion, unless they're at absolute zero. We haven't been able to successfully measure any particle at rapid zero or at absolute zero. The next thing is they move in straight lines unless acted upon by outside forces, which means it's sort of like a pool ball theory. If number 7 hits 8, then that's going to cause number 8 to bounce around, maybe hitting 3, but 3 is going to continue in a straight line unless it hits another ball or the walls of the container. And so also built into this theory is the idea that the pressure that a gas exerts is due to collisions with the outside walls of the container. And it's going to be dependent because the more molecules you have, the faster they're moving, the more interactions with the walls of the container. So it's all kind of linked together. But this idea that they're going to be constantly moving and they're going to be colliding with each other and colliding with the walls of the container, but the pressure is due only to that interaction with the walls of the container, not due to these individual interactions. And so you don't have to measure that. You just have to measure what's the interactions with the outside edges. The third theory is the idea that since particles are moving so fast and they're so far apart, there's not a lot of traction between the particles, so they don't attract each other. It's sort of like how you might have a friend who says, oh, I can never find this person, I'm never a blah, 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 and they're just whining because they can never find somebody, blah, blah, blah. But you know what? If they're not putting themselves out there, that's their own fault, okay? Because it's with these atoms. They don't have enough time to actually have any attraction. And we'll find out later, there is still a degree at which the particles interact. But for the most part, there's not a lot of attraction between molecules. They're like speed dating. Hi, bye, and they just run on by. Okay, there's not time for the interaction. And so therefore, it is assumed, at least in this theory, that there's not a lot of attraction between particles. The last theory is what allows us to relate the energy or the motion of the particles to temperature. The idea is that temperature is related to the motion of the particles. As molecules move around, it's because they got hotter. And as things got hotter, they moved around faster. And as stuff moves around faster, it's getting hotter. And so it's just like this poor racquetball player here who looks like he's a little bit tired. And it's probably because he's been running all the way around the court. Okay, so the more motion, the hotter you get. And that's the same thing that applies to the motion of gas atoms. All right, 2 vocabulary words here. Diffusion is the intermingling of gases, whereas effusion is the escape of gases through teeny tiny holes. So when you think about diffusion, I think about the idea of being on a bus and maybe somebody decided that they were stinky and they sprayed some perfume. And then the whole rest of the bus is going, what is wrong with you? Because we all smell your gross perfume. Please stop doing that. Okay, that's diffusion. The idea that a gas will always flow from an area of high concentration to an area of low concentration, which is what these two things are trying to show you. They're one, showing you a fusion because the gases are escaping through this little teeny tiny hole, but then number two, oxygen has a high concentration here and a low concentration. It's 0 over here. Nitrogen at the same time has a high concentration here and a low concentration here. And so what's going to happen is oxygen is going to diffuse from a high concentration to a low concentration region, whereas nitrogen is going to diffuse from a high concentration to a low concentration until an equilibrium is reached, which is what you see here, where there's an approximately equal number of each gas particle on each side, and the total net sum of each is going to be about the same, half atmosphere from each one, giving us still 1 atmosphere on each side. Okay, and that's because it started out with 1 atmosphere. All right, so now how is temperature related to kinetic energy? So this is a graph that's showing you what's called root mean square speed, or average molecular speed. If you go for a run, you're not consistently going the exact same pace every second of the run. You have highs and you have lows. It's the same thing with molecules. If you think about it, if this one was going so fast and it flew into this molecule, which was going slower, it's going to give some of its kinetic energy to this molecule, which is now going to be faster, and it in turn is going to be slower. And so when you're talking about kinetic energy and about the speed of particles, molecules or atoms, gases, will always have an average speed. This is the average speed at 25 degrees Celsius, and the top of this peak is the average speed at 1,000 degrees Celsius. So notice at a lower temperature, you're having very much lower molecular speed. So it's like 400, if I could draw a straight line. It's like 400 meters per second, whereas the average speed at 1,000 degrees Celsius is closer to like 850. And so it's a lot faster as you increase the temperature, but look at the average distribution. How wide something is tells you that there's a greater standard deviation, which means there's some molecules that are going, whoa, super crazy fast, and there are other molecules that are still going slow. And so you get an average distribution of molecules. But it's this average speed that is related to our temperature. So let me ask you this question. If you had 1 mole of each of these at the same temperature, which would have the highest average kinetic energy? Think about it for a second and then make a guess. I hope you thought back to this graph where you might have noticed that this graph had nothing to do with which molecule we're talking about. And that's because your kinetic energy is 3/2 times the gas constant times your temperature. This means at the same temperature, all have the same kinetic energy. This is important, very important. Okay, but if we look at a very similar question, but it's different, if you had 1 mole of each of these at the same temperature now, which would have the greatest velocity, or root mean square speed? That's a little bit different of a question. So yes, we can look back at this graph, but this is now talking about molecular speed, just as it was before, but it's not entirely dependent on just the temperature. And that's because of this good equation right here. Kinetic energy is 1/2 mass times velocity squared. So if you know the temperature, then you know that they have a same average kinetic energy, because on this one you said same temperature, same kinetic energy. So they all have the same kinetic energy, but what do you think these variables stand for? We have a mass and a velocity. So what that means is if we have a large mass, we have a small velocity. And so if we're looking for the greatest velocity, then we want the smallest mass. And so you look at each of these molecules and figure out which one's smallest, and that would have the greatest velocity. And so in looking at all of these equations, thinking about these graphs, just note temperature and kinetic energy, they're going to be very even, but actual velocity, because stuff that is lighter moves faster, that is not going to be the same for each of them. And so because of that, we have something called the root mean square speed. And this is a real measure of an average velocity, if you will, of the gas in the sample. And so this is the graph for oxygen specifically, but we also can use and find this for anything. Now, so there are some very important distinctions to make. Number one, this time your R needs to be 8.314. Why? Because of this main part right here, meters per second. We're looking for speeds, and so we want it to meters and seconds to be part of the equation. And then this right here, your molar mass, must be in kilograms per mole. Those are the two important pieces of this puzzle. If you miss any part of this question, it's normally one of those two. And so then it's just a matter of plugging in the variables that you have obtained. So let's do an example. If we're asked to calculate the root mean square velocity for the oxygen molecules in a sample of gas at 32.3 degrees Celsius, we can. So let's try this. What is, first off, my molar mass? Big M, little m. It needs to be in kilograms per mole. So we know that the normal way we calculate it is 31.998 grams of O2 per mole. But we need that to be in kilograms per mole. So remember, 1 kilogram is equal to 1,000 grams. And that equals 0.0319998 kilograms per mole of oxygen. All right, now we can plug all of this in. Mu equals the square root of 3 times my R, 8.314 kilograms times meters squared over seconds squared times Kelvin times mole. All over plus times temperature. Can't forget our temperature. Turn 32 degrees into what unit? Kelvin. So if we're going to turn that into Kelvin, it's going to be 305.45 Kelvin, with that being our last sig fig there. Square root sign is over all of it. And then our molecular mass on the bottom, 0.031998 kilograms of oxygen per mole. See what cancels. Mole, mole. Excuse me. Kilograms, kilograms, Kelvin, Kelvin. We're ending up with meters squared over seconds squared. But that's not what we want. I thought it was meters per second. Oh, square root. So square root gets rid of both of those squared signs, leaving you with just meters per second. So if we do all this math, type in your calculator, make sure you can do this, we end up with 487.9 meters per second. And that's my final answer. Alrighty, so let's look one more time at a slightly similar problem that'll combine this concept here of diffusion and diffusion with that equation that we just looked at, that of the root mean square speed. So the idea here is can we figure out what the rate of effusion of one gas is compared to another? Absolutely. Just set up a ratio and solve. But the idea would be, all right, if we have two gases and they're mixing together, wouldn't their temperature in this top part all be equal? Absolutely. And so they cancel out, leaving us with, and notice they do switch. It's because this was on 1 over, and so if you just take 1 over something, it's just putting it on top. So algebraically, this converts to this equation here. And so the idea is if you want to think about which one will travel faster through a hole, you're going to be able to based on the molar mass of a compound. So here's a question that's very similar. Which do you think will travel faster through the same hole at the same temperature and pressure, a light or a heavy molecule? What do you think? All right, so we know from before, if we increase our mass, we are decreasing our velocity. And then, this is your mu, right? So if we increase our molar mass, we are decreasing our root mean squared speed. So if larger molecules have a reduction in both velocity and root mean square speeds, the thing that travels faster through the hole is a light molecule. And one of the fun ways that they found this out was they wanted to perform a reaction and see what happened. And so what happened is they placed ammonia on one end of a piece of glass, and they wetted a piece of cotton with hydrochloric acid on the other. And they knew that if these two, since they were both wet liquids, they would both release gaseous vapors containing the molecule that it was wetted with. And as these molecules moved all around, they would eventually interact. But what's cool is it forms a solid when it interacts. So they were able to tell at which place in the gas column they collided. And they found that it collided and formed a white precipitant right here, and that indicates where ammonia and hydrochloric acid met. But what was interesting is they expected it to be in the middle, but it wasn't. And the reason for that being is the differences in mass. And so this ammonia is much smaller than that of hydrochloric acid. And so it traveled faster, so it made it further in the tube than hydrochloric acid did in the same time. And so this was just one experiment that showed them how they could look at diffusion, fusion, and kind of figure out this idea between gas movement and velocity of particles.